Hello and welcome everyone. I am Himanshu Mishra welcoming you on this online platform of Gallup classes. Today we are going to discuss the simple harmonic motion, and in the simple harmonic motion we are going to discuss so in this video we are going to discuss the energy associated in simple harmonic motion, or basically the energies in simple harmonic motion. So our topic of concern is energy in simple harmonic motion. So we all know that the mechanical energy or the total mechanical energy consists of potential energy and kinetic energy. So in this, first of all, we are going to discuss potential energy. So the basic formula of potential energy is F is equals to minus du by dx. And in the simple harmonic motion, the F consists of F is equals to restoring force, which can be written as minus k into x, where x is displacement. In our earlier session we have used y as displacement, but it will not make any change. So F is equals to minus kx, so substitute the value here. Minus kx is equals to minus du by dx. So if we cancel out the negative sign, and du will become kx into dx. Now on integration, on integrating, this will become integration of du is equals to integration of kx into dx. So integration of du will become u and k will be constant, and the integration of x will become x square by 2 plus a constant c, because this is indefinite integral. Now going further on this, at mean position, at mean position x is equals to 0, then u is equals to u naught. So if we substitute the value here, so u naught is equals to k into 0 square by 2 plus c. So the value of c will become u naught. The so potential energy u is equals to half kx square plus u naught. So this is potential energy u. Okay. Now the kinetic energy in simple harmonic motion. Kinetic energy in S.H.M. Tell me the equation of velocity v. The v can be written as a omega cos omega t, and which also can be written as omega into under root a square minus x square, where a is amplitude, x is displacement, omega is angular velocity. Now we all know that kinetic energy is equals to half m v square. Substitute the value of v here, so kinetic energy will become 1 by 2 m a square omega square cos square omega t, or which can also be written as in terms of x. So kinetic energy will become 1 by 2 m omega square a square minus x square. Is this okay? So this can be the equation of kinetic energy. Now the total energy, or the total mechanical energy in S.H.M. So total mechanical energy in S.H.M. Now we all know that total mechanical energy can be written as potential energy plus kinetic energy. So potential energy plus kinetic energy. So total mechanical energy is equals to potential energy if we consider, see, potential energy if we consider U is equals to U naught plus half kx square, U naught plus half kx square plus the value of kinetic energy half m omega square a square minus x square. So half m omega square a square minus x square. Okay, so if u naught is equals to 0 and k is written as m omega square, we all know the famous formula, omega is equals to under root k upon m. So from that formula we have discussed this. So if we substitute the values here, total mechanical energy will become half m omega square into x square plus half m omega square into a square minus x square. If we multiply this inside, so total mechanical energy is equals to half m omega square x square plus half m omega square into a square minus half m omega square into x square. So we can clearly see that half m omega square in positive sign and half m omega square in negative sign. So we can cancel these terms. So the total mechanical energy will become, total mechanical energy will become half m omega square a square. Is this okay? So the total mechanical energy half m omega square a square. So from this equation we can say a few things, that the total mechanical energy will remains constant. So the total mechanical energy remains constant, or we can say that there is no loss in mechanical energy, or basically this is conservation of mechanical energy. Clear? Okay, there is a question. So now if we are going to draw the graphs, or so this is displacement axis or x-axis, and this is energy. So can you tell me what is the formula of energy or the potential energy? The potential energy can be written as half m omega square into x square plus u naught. So if we draw the graph of potential energy here, so potential energy the graph will look like this, and this intersection is u naught. So this is the point which is u naught, and this is the graph of potential energy. See, this is the graph of potential energy because the potential energy is directly proportional to x square, and the graph will be parabolic. Is this okay? Now, if we draw the graph of total mechanical energy or the total energy and displacement, so this is x and this is energies associated with all the terms. So if u naught is 0, the potential energy can be drawn like this, and this is the maximum potential energy at x is equals to plus a and x is equals to minus a. So this is basically the graph of potential energy. Now if we draw the graph of kinetic energy, so the graph of kinetic energy will look like this. So this is the graph of kinetic energy. Is this okay? See, this graph is of opposite of potential energy. See, the equation of potential energy can be written as u is equals to half m omega square into x square, and kinetic energy can be written as ke is equals to half m omega square into a square minus x square. So we can clearly see that there is a negative sign ahead of x square. So this will be the opposite parabola of potential energy. Is this okay? So we can see clearly that at mean position, see, at this is mean position. So at mean position, kinetic energy is maximum and potential energy is minimum. And if we draw the total mechanical energy, so the graph of total mechanical energy will look like this. So this is total mechanical energy, and which is constant. Is this okay? So we have discussed all the important thing. Now the first question, the total energy of a body executing S.H.M is E, then kinetic energy when displacement is half of the amplitude is. See, in this question the examiner have told that the total energy of body executing S.H.M is E, so E is equals to half m omega square into a square, and then kinetic energy when displacement is half of the amplitude, so kinetic energy can be written as half m omega square into a square minus x square. So substitute the value of x when displacement x is half of amplitude, so basically x is equals to a by 2. Substitute the value here, so kinetic energy will become half m omega square into a square minus a square by 4. So basically the square of a by 2 is a square upon 4. So kinetic energy will become half m omega square into 3 by 4 of a square. So we can rewrite it as kinetic energy is equals to half m omega square into a square multiply with 3 by 4. See, we can clearly see that half m omega square a square can be written as capital E. So kinetic energy will become E into 3 by 4. So we can see 3E by 4 will be our answer. So 3E by 4 is the option C. Okay. Now the kinetic energy and potential energy of a particle executing simple harmonic motion will be equal than displacement is. Okay. So in this question, the potential energy and kinetic energy are equal. So basically potential energy is equals to kinetic energy. We can substitute the value of potential energy half m omega square into x square is equals to half m omega square into a square minus x square. So we can cancel out these terms, half m omega square, and the remaining part will be x square is equals to a square minus x square. So we can rewrite it as a square is equals to x square will come this side and it will become 2x square. And from here we can substitute the x square is equals to a square by 2, or x can be written as a upon under root 2. So the answer will be a by root 2. Option C is correct here. Okay, in a simple harmonic oscillator at mean position, kinetic energy is maximum and potential energy is minimum. See, we have drawn this graph. This is x, this is energy, and this was the graph of potential energy, and this was the graph of kinetic energy. So at mean position, this is the mean position. So at mean position, we can clearly see that kinetic energy is maximum and potential energy is minimum. See, I am using again and again the word minimum. I am not using zero. It is not necessary that the potential energy at mean position is zero. Now we are going to discuss the potential energy of a particle oscillating on x-axis is given as u is equals to 20 plus x minus 2 square, where u is in joule and x is in meter. Total mechanical energy of particle is 36 joule. Okay, then mean position and maximum kinetic energy of particle will be, C. F can be written as minus du by dx. So if we differentiate this, the differentiation of 20 will be 0, and okay, I am rewriting it, minus d by dx of 20 plus x minus 2 ka square. ठीक. So f is equals to, the differentiation of 20 will be 0, negative sign ahead, 0 plus 2 into x minus 2. So f will become minus 2 into x minus 2. We all know that at mean position, see, at mean position, f is equals to 0. So the mean position will be 0 is equals to minus 2 into x minus 2. So from this equation we can say x is equals to 2 meters. So the option will correct be 2 meter. So option A or D will be correct. Option B and C will be incorrect. So we are going to check further that A and D. So now at mean position, the potential energy U will be minimum. So the minimum value of potential energy U min is equals to 20 plus x. The value of x is 2, so 2 minus 2 square, so the minimum potential energy will become 20 joule. So minimum potential energy at mean position is 20 joule. Now we all know that at mean position U is minimum and kinetic energy will be maximum. Kinetic energy will be maximum, but we all know that the total mechanical energy of particle is 36 joule. So total mechanical energy is equals to U minimum plus kinetic energy maximum. Substitute the values here. So total mechanical energy is 36 is equals to U minimum is 20 joule plus kinetic energy maximum. So we can find the value of kinetic energy maximum can be 36 minus 20. So the answer will become 16 joule. So answer will be 16 joule. So 2 meter and 16 joule at option A will be correct. Now there is a graph. The variation in potential energy of harmonic oscillator is shown in figure. The spring constant will be. See in this graph at y is equals to 20 mm, the u is equals to 0.04. So we all know that potential energy can be written as half m omega half kx square. In this question spring constant k is asked, so half kx square. The value of u is 0.04 is equals to half into k into x. The value of x is 20 into 10 to the power minus 3. See, the value is given here is 20 mm, which is equals to 20 into 10 to the power minus 3 meter. Okay, so from this equation, this is square. So k is equals to 0.04 into 2 divided by 20 into 10 raised to the power minus 3 whole square. So kinetic energy will become 0.04 into 2 divided by 20 into 20 into 10 to the power 6. So kinetic energy will become spring constant k is equals to 4 into 2 into 10 to the power 2 divided by 2 into 2, which is 4. So the answer of k will be 2 into 10 to the power 2 Newton upon meter. So answer will be 2 into 10 to the power 2 Newton upon meter. Option B will be correct. So that's it for today, guys. We will discuss the remaining question in our next session. Thank you, everybody. We'll see you tomorrow.